Hey students, astronomers, welcome. This is our lesson for Thursday of our first week of school, fall 2020. And our lesson today is about navigating the night sky. And again, if you were a synchronous student yesterday for our first day of school, today you are viewing our lesson asynchronously. And again, if you're watching this video, obviously you've already found it, but again, just for future reference, one way to access your daily assignments and videos and whatnot is to go to to go to the calendar. You can click there, and then just click on the block for a given day that has the name of the day in it. So for example, this block says Thursday 8 slash, and the title is sort of cut off there, but it says Thursday 8/13/20, navigating the night sky. And then if you click more, it'll give you the ability to go ahead and click on the assignment for the day. And you can read about it, find out what you need to do. Another method you can use, and you might prefer this, maybe not, but the little content window that we have here, again, we're just starting the school year. We're in Unit 1, so you can click on Unit 1. And again, each unit folder is going to be broken down into both daily lessons / assignments, and then also reference materials. So you can go to daily lessons and assignments. Again, today we're talking about Thursday 8/13, and again, get to the same document that we saw a moment ago. So all that said, let's go ahead and get to the lesson itself. And I will turn off my video so that my face isn't blocking anything. Okay. Here we go. All right. So navigating the night sky. Mr. N. Williams, that's me, fall 2020. All right. So again, in the previous lesson, yesterday, first day, we talked about this idea of the celestial sphere. We talked about some basic markers on it to kind of give us some bearings. We talked about the fact that just like the surface of the Earth, we can mark it with a North Pole, a South Pole, and an equator, among other things. The celestial sphere has its own equivalents of those markings. We have the celestial North Pole. Again, this diagram leaves it out, but we also have going the opposite direction, a celestial South Pole, and then we have the celestial equator. All of those items, all three of those items, those markings, just project outward from Earth to wherever they happen to point to in the night sky. And of course, we can imagine that eventually they reach some end, which we consider to be the surface of the celestial sphere. Again, the ancients would have thought of that as an actual structure. We just use it as a helpful navigation description. All right, so, oops, sorry about that. All right, so the first thing we're going to talk about with how to navigate the celestial sphere. In other words, let's say you've seen something really cool in the night sky. You have a new favorite star or something like that, and you want to be able to describe to somebody where they can find it. Well, just like how we can locate something on the surface of the Earth using latitude and longitude coordinates, we have the same basic method that we can use in the night sky, but we don't use the terms latitude and longitude, although we will have these equivalent ideas. And the first one is right ascension. Right ascension, which you can see is abbreviated either as just RA, or sometimes they use the Greek lowercase letter alpha. That's their version of the letter A. And it's the celestial equivalent of longitude. And so again, don't forget, longitude is measured vertically on the globe from north to south pole. And similarly, all of these little markings show you could fill them in with vertical lines going from the celestial South Pole to the celestial North Pole. In fact, let me flip ahead for a second, just because this one diagram maybe shows that off a little bit better. So again, these vertical lines from pole to pole, those represent lines of right ascension. Now, how we measure right ascension. This one's kind of strange because it sounds like you're talking about units of time. So, but we measure right ascension. The most basic unit is hours. Or I should say that's the most encompassing unit. An hour of right ascension is a big chunk of the sky. And there is a reason why it's called hours. We'll come back around to that in a moment. But we measure it in hours. That's the biggest amount. And then minutes is a little more precise. And then seconds is even more precise, rather than degrees, minutes, and seconds, which is what you would use with just angles in general. So Minutes and seconds here refer to smaller divisions of the hour/degree than we are typically used to. And we'll come back to that on slide 11. We'll talk a little bit more about these angular measurements. Now, one other thing to be aware of is that right ascension begins on the celestial sphere with the 0-hour line, which is directly above any location along Earth's prime meridian. The hours increase in amount in an eastward direction until you reach 24 hours, which is the same as the 0-hour line. Typically, because the 0-hour line and the 24-hour line are the same line, most of the time the 24-hour line is not going to be marked as such. It'll just be marked as 0. And again, this diagram kind of helps show you what's going on here. So again, if this is the 0-hour line right here, and again, if we were to sketch it out, it would go from here all the way to the North Pole, then going eastward, a little bit further, we would reach a 1-hour line. And then the same amount again, we'd get to the 2-hour line, 3 hours, 4, 5, 6. We could keep going all the way around. We come back around to this side. We eventually get to 21, 22, 23, and then 0. Now, the reason, again, I said there's a reason why these measurements are called hours. And that's because the distance between 2 hour markings of right ascension is how much the Earth turns in an hour of time. And of course, you all know how long it takes for the Earth to make one rotation, because that's how long a day is. It's 24 hours. So it makes sense that, okay, well, if we take one rotation of the Earth and divide it up into an equal number of parts based on how long each one takes to make an hour of time, well, we're going to get 24 divisions of the sky as a result. All right, the other measurement we use for navigating the night sky is declination. Again, that can be abbreviated as DEC. That does not mean December in this case, although it does look like it. We also can use the Greek letter delta. Again, this is the the lowercase form version of delta. It looks kind of like a lowercase d, but also kind of different. So that's what it appears like, just in case you do see it. And again, this is the celestial equivalent of latitude. And so just like how lines of latitude on the Earth are basically northern or southern versions of the equator, this is also true for lines of declination on the celestial sphere. So if the celestial equator represents 0 degrees, then any parallel line around the celestial sphere north of that is going to be measured in some larger number of degrees, with a maximum of 90, and that being the north celestial pole. And of course, we can run the reverse situation going from the celestial equator south toward the south celestial pole. One thing you'll notice, though, just to differentiate between similar numbers of declination in the northern hemisphere versus the southern hemisphere, is that all of the numbers for declination in the north are measured with a positive value, and all the equivalent measurements in the southern hemisphere are measured with a negative value. So if you see a declination with a negative number, you know right off the bat that you're talking about something that is further south than the celestial equator. All right. One other thing, a good example to use here is Polaris. Polaris, again, being the North Star. We talked about it in yesterday's lesson. It is almost exactly at the celestial North Pole, but again, we use that word almost. So here's an example of where to find Polaris, at least if you had to use a star chart. You would have a right ascension of 2 hours, 31 minutes, and 49.09 seconds. And again, what that means is that it would be 2 hours of right ascension east from the celestial prime meridian. Its declination, like I said, almost 90 degrees. It's 89 degrees, 15 arc minutes, and 50.8 arc seconds. Sirius, the brightest star in the sky, its right ascension is 6 hours, 45 minutes, and 9 seconds. So again, a little further east away from the prime meridian than Polaris is. And its declination is only 16 degrees, 42 arc minutes, and 58 arc seconds. So again, its declination, 16 versus Polaris's of 89. And again, that kind of explains why Polaris is almost right at that north celestial pole, pretty much is. But again, if you look at the markings on our diagram here, you can see if we go south from the north celestial pole, down here, this is where positive 60 declination would be, 60 degrees of declination. Down here, positive 30 degrees, and of course the equator being 0. So Sirius sits about halfway up between the celestial equator and the positive 30-degree declination line. So right about where I have the pointer now. All right, let's take a moment to talk about these angular measurements, because a lot of times we don't really make use of these kind of things in everyday experience. So the descriptions I've been giving so far may not have made a lot of sense. Hopefully this will help explain it, at least on a basic level. So one thing that we can all kind of familiarize ourselves with in terms of angular measurements is that they are based on portions of a circle. And again, hopefully one thing you remember is that a circle in total is divided into 360 degrees. However, if we apply that idea to the night sky, we run into a bit of a problem. If we take the night sky, the celestial sphere, and we divide it into 360 degrees, and by the way, when we would do that, we would be using lines of right ascension, because those are the lines that go from north to south pole. They're a lot like lines of longitude. Anyway, the problem we get is that even though we would be dividing the sky into 360 different vertical segments, north to south, the sky is so big and there are so many different celestial objects, again, mostly stars, planets, also all kinds of other things up there to see, that we can actually see a lot of stuff, even just between two different degree lines next to each other. So just describing the position of a celestial object like a star or a planet with just this basic level description of degrees is not actually that helpful, because there's going to be so many other things near it in the night sky that can be described with the same number. So let's see, we have to describe the angular spaces within that 1 degree line. And you can kind of see what we're talking about here by looking at this diagram. So again, if this represents the night sky, or at least a circle within it, then 1 degree, 1 arc degree, again, the further out we go, the more space that covers, and again, more stars could be within that little viewpoint. So what we do then is we take a degree, 1/360th of a circle, and we divide it into 60, what we call minutes of arc, or just arc minutes. And that's where you can see in the diagram, that's where we go from here to here. Again, this little sliver is 1 arc degree, or just 1 degree, as we would normally say. But if we take a zoomed in look at it and divide it into 60 individual slivers, one of those would be an arc minute. Or again, sometimes you hear people say minute of arc. It's a fairly common saying. So, and it shows that a single quotation mark is the symbol for minutes of arc. So right here, when it says 60 with that little apostrophe or quotation mark, that's how you should read it. You should read that as 1 arc minute, or 1 minute of arc. Now, here's the thing. Even an arc minute is still going to be, at long distances of viewing in the night sky, is still going to be wide enough or big enough to contain lots of different stars and nebulae and all that to look at. So sometimes we still even need to be more specific about a location in the night sky. And so we can do the same thing again. We can take the arc minute, zoom in on it, and divide it once more by 60. And if we do that, just like how if you divide a minute of time by 60, you get 1 second, here we get 1 arc second. Or again, sometimes you hear people say a second of arc, excuse me. So here's the thing though, if you actually do the math here, if we divide 360 by 60 and by 60 again, that means that 1 arc second is only equal to 1/3600th of a degree. So it's a very, very small sliver of the night sky. This is where we can start to be, usefully precise with describing where a star might be located. And that's why we want to take a minute to point that out, because a lot of times if you look up these coordinates for stars, you're going to see that level of precision. All right, so another thing here, like what is it we can see exactly in the night sky? The model of the celestial sphere makes an assumption, and this is not true, but it makes an assumption that all stars, except of course the sun, are at the same distance from the Earth, just in different locations, or different directions, excuse me. So again, if we go back here, so again, if you can imagine, like on this diagram here, this blue surface being dotted with all the stars, again, except for the sun. Of course, actually, in this diagram, they've even aligned the sun to it as well. That's kind of, again, mentally the idea of the celestial sphere. Like we said, this, however, is not really accurate at all, because in reality, we might be looking at two stars right next to each other on the celestial sphere. And in fact, they might be very, very, very far apart from each other in terms of depth. A very good example of this is with constellations. A lot of constellations, not all, but most of them, are made up of stars that, while some of them might be kind of at similar depths compared to each other from the Earth, some of the other ones are going to be either much, much farther away or maybe much, much closer. And this is actually, you might recognize this pattern in the little sliver of the night sky here. This little section is supposed to represent part of the celestial sphere as we see it. And you might recognize the pattern of being the constellation of Orion. There's Orion's belt in the center, the red star Betelgeuse at the top left, Orion's right shoulder, that's what it would be, and so on. So here's the thing. Even just the three stars of Orion's belt, this is Delta Orionis here, Epsilon Orionis, I believe this is Zeta Orionis, if I recognize that correctly. Those three stars, I mean, you can tell these two are kind of at similar distances from Earth, but this one is much, much further out. And also, if you look at both Alpha, which again, that's the star Betelgeuse, or Gamma Orionis, they're a lot closer to Earth than any of the other ones. So when we look at the night sky, when we look at the celestial sphere, the sort of visual assumption we have to make, because to our appearances, or sorry, to our eyes, it appears that all the stars are at the same distance. We have to remember that even within one constellation or a little cluster of stars that appears to our eyes to be close to each other, they may not, in fact, really be close to each other in real space. Sometimes yes, many times not at all. All right, we're going to take a minute now, kind of shift gears just a little bit. We're going to talk about our local or personal night sky. So all of the measurements and markings and that sort of thing that we've been talking about so far are things that are standards. In other words, everybody on the Earth, if they want to look at the celestial North Pole, there's a particular direction they have to look. And again, you would not even be able to see it from certain parts of the Southern Hemisphere, most parts of the Southern Hemisphere. So anyway, point being, we can also, because we can travel to different parts of the Earth. We can go to different places here in Georgia. We can go to different places here in the United States. We can go to other countries and continents and so on. We need to be able to also describe just how the sky looks to us. What our local or personal night sky is. This makes for very useful stargazing. So different locations in the world produce different night skies. For example, like just a really simple basic difference, again, to a typical person living somewhere in the Northern Hemisphere, your sky is going to look pretty different to someone living in the Southern Hemisphere. So anyway, this means that every observer has a few sky locations and measurements relative to themselves. So note that unless you are at Earth's north or south poles, none of these align with the permanent features of the celestial sphere. In other words, again, like if I was hanging out with Santa Claus and went to the North Pole and looked straight up right from the North Pole, then the celestial North Pole would be right above me. But here in Georgia, that's not the case. If you go outside at night, right now, or tonight, whatever, whenever you're watching this, and you look for Polaris, again, which is roughly where the celestial North Pole is, it's not going to be straight overhead because you don't live at the North Pole. It's going to be off at a particular angle. So what you can do, though, we do have a term you can use for describing what point of the sky is straight above you, and that's this term here, the zenith. The zenith, again, is the top of the local sky. At Earth's North Pole, again, like we said, this would be the celestial North Pole / Polaris. But again, that's only if you're at the North Pole. Most of you are not hanging out there, so your zenith is going to be some other location on the celestial sphere. By the way, just a kind of general terminology sort of thing, if you hear people talking about zenith in a non-astronomical context, like a very common turn of phrase might be like somebody describing the zenith of so-and-so's career. Zenith, since it's the high point of someone's personal sky, it also can just mean the high point of a lot of other things. So sometimes that term gets generalized. Now, the opposite of your zenith is the nadir. Some people say nadir. I'm pretty sure nadir is more correct. But anyhow, The nadir, which is not shown in this top diagram, but it is down here, it is the point directly below you. So in fact, wherever you are, you actually can never see the nadir of your personal night sky because it's actually straight through the ground below you. Like if you imagined a line going through your feet, down through, straight through the center of the planet, out the other side, to the celestial, or I was going to say to the celestial South Pole. That's only true if you're at Earth's North Pole. Anyway, it straight into the sky. That would be your nadir. And again, similar to how zenith kind of generally means the high point of something, nadir means the low point of something too. All right, so the meridian. Now, this is not the same as the prime meridian of Earth, other than the fact that it also traces a path from north to south. But your meridian is simply where, it's the line through the sky tracing a path from north to south, closest to overhead. And that's what's being shown on the outer edge of this diagram. If you'll notice, they show north is off to the right here, south is off to the left. So this line going across the center of this person's sky from north to south, that's your celestial meridian. You're going to see in the video today that if you were to just lay down in a field and look up at the night sky, the celestial meridian should just divide your sky into two different halves. And yeah, it's also shown in this bottom diagram in a similar way because they flip this around. They show north to the left, they show south to the right, and either way, that means that the celestial meridian goes across the top of this sphere. Now, the horizon. This is one you have some familiarity with, I'm sure, because the horizon is simply the horizontal line where the sky and the earth meet from your perspective. In other words, if you are in a roughly flat area, things like trees and buildings really obscure the horizon. But if you're in a relatively flat area, out at the ocean, whatever, this is very easy to tell. You look out and eventually you can see a point where if you look up above it, there's sky, and if you look down below it, there's ground or water or what have you. And of course, the major takeaway with the horizon for astronomers is that it is what blocks your view of anything below it. You can be at any point on the planet and you're going to be looking around and there's a horizon that's going to block your view from looking any further down. And of course, this is also playing into why you don't see the nadir of your current point. Now, another thing we need to talk about real quick is altitude and azimuth. Now, altitude is a familiar term, generally it just means like how high up something is. For astronomy and for your personal night sky, it's pretty similar, but this time it's an angular altitude. And so what we do is we measure how high something is in degrees between 0 and 90 of a star or a planet, how high it is from the horizon. So the altitude is a measurement relative to the horizon. The horizon would always represent 0 degrees of altitude, and the higher something is above the horizon, the greater the angle will be. And again, similar to declination, we can actually still talk about negative altitude, because even though we can't see stars that are below the horizon, we still can know that they're there, and we can describe their current position. So, for example, maybe before they've risen up into the night sky, or maybe just after they've set. So my point there is that if you can see a star in the night sky and you're describing its altitude, that means it's above the horizon, and you can describe its altitude with a positive value. So for example, this diagram here, the star they're looking at is about halfway up to the zenith, which is where you would have 90 degrees. So the altitude of this star is about positive 45 degrees. All right, the azimuth. This one's a little different. It says how far a star or a planet is in degrees between 0 and 360 from north going clockwise in an eastward direction. So that's a lot, to me at least, that seems like a lot more complicated description. But again, basically, if you're measuring the azimuth of a star, it's basically telling you which direction to look in terms of north, south, east, and west. Again, maybe I'm staring south and my friend says, no, it's over this way instead. And they point me off to the east. So in this diagram, again, the star is right here. And you can already see we've described that north is off to our right as viewers of the screen. And so what the observer down here has to do, they have to go and look at north and then decide how many degrees of a circle is the altitude of their star from that north. And again, if I were just to kind of make a guess, I'd say this is about, yeah, this is still probably about 45 degrees, because don't forget, one quarter, east here would be 1/4 of a circle, and that would be 90 degrees. And so this is still about half of that, 90 degrees, making it about 45. Just another example here, it says a star that is directly south of your position would have an azimuth of 180 degrees. That would only actually be true if if north was directly behind you. Sorry about that. All right, a little sidebar on distances, and then we are almost done for today. All right, so the universe is big enough that we can't really understand its size very well. In fact, one of the bigger arguments that even still isn't totally settled now has been about whether or not the universe is something that is infinite in size, or it does have a limit to its size, but okay, it's still going to be a very, very great size to it. So anyhow, we have developed units of measurement that are, of course, much, much, much larger than anything we would use here on the Earth, like miles or feet or anything like that, to help make sense of the size of the universe. Now, probably what most people would say is the most basic unit of measurement for the universe, for the cosmos, is called the AU, or the astronomical unit. And this one is, first of all, it's kind of small compared to the others. And it's also something that uses our situation as its reference point. And what by that I mean, it's the mean or average distance between the Earth and the Sun. And if we were a civilization that lived on Mars, that might seem kind of arbitrary. Like, why would we use a unit based on the distance between the Earth and the Sun? But well, guess what? We don't live on Mars. We're here on Earth. We are terrestrial creatures. So it kind of makes sense that we would maybe use something like that. But anyhow, this distance turns out to be 149.6 million kilometers. In more familiar miles terms, that's about 93 million. So again, that's a long way to go. The sun is about 93 million miles away, at least on average. We'll talk more about the average part in a later lesson. But this is most helpful, the AU, the astronomical unit, is most helpful when discussing distances within our solar system. Because actually, even some of the things that orbit the sun are far enough away to be measured in tens of AUs, or sometimes even hundreds of AUs. For example, Neptune, if I'm not mistaken, is about 30 AUs away from the sun. Again, Earth is 1 AU away. Mars is a little bit farther out at 1.52 AU. And of course, that also means that Venus and Mercury both have distance values of less than 1 AU compared to their, measuring how far they are from the sun. Now, these next two distances are a lot longer, so they're a lot better for talking about distances between stars, that sort of thing. And of course, the more famous one is the light year, or LY for short. And this is defined as the distance a wave of light, or any other kind of electromagnetic wave, radio waves, X-rays, whatever, can travel in a vacuum in 1 year. So, and again, I know some people get mixed up and they think light years describe an amount of time because the name kind of sounds like that. But if you kind of wrap your head around the definition one time, it kind of keeps making sense after that. Again, how far can a light wave go in a vacuum, meaning nothing's getting in its way to slow it down, in 1 year? So since the speed of light, which we represent with the lowercase c, is about 3 times 10 to the 8th meters per second. Now I want you to think about that for a second. 3 times 10 to the 8th. That's scientific notation. That means 3 with 8 zeros after it. So again, one light wave can go 3 with 8 zeros after it meters in 1 second. That's its velocity. Because that's the speed of light, a light year is equal to about 9.46 times 10 to the 12th kilometers, or again in miles, that turns out to be about 6 trillion miles. If we equate this to AUs, which we said were a smaller unit than light years, it's equal to about 63,241.1 AUs. Again, like I said, this is a more useful unit when talking about distances between stars. That being said, we have sort of an alternative to the light year. We have the parsec. And now parsecs Not, I wouldn't say nearly as famous as the term light year, but a lot of people know it in large part because of Star Wars. There's a big sort of, I don't want to say controversy, but a lot of people know that in the first Star Wars movie, the first one that came out chronologically in the 70s, Han Solo, Harrison Ford's character, he brags about making the Kessel Run in, about like 12 parsecs. He says something like that. And of course, the context of the statement, he's saying, "Oh, I did it like really quickly. I did it in a short amount of time." That's clearly the implication of what he's saying. The problem is that kind of like how, again, the light year sounds like an amount of time, and parsecs, which stand for parallax seconds, they also sound like time. You can see kind of why they might mess up with that. Again, like the light year is a unit of distance, so is the parsec. And again, it's called a parallax second. That's what parsec is short for. And we're going to talk more about parallax later. But the second here, again, the reason why it's not a unit of time is because it's meant in the context of arc seconds, like we talked about earlier with measuring angular distances. All right, so a parsec is the distance to a star when a right triangle is formed by the star, and that would be over here at this end of this diagram. So a right triangle formed by the star, the sun, which would be the center of the circle, and the earth, which is on the edge of the circle. And the star has an angle of about 1 arc second, which is a really tiny angle. Don't forget that. 1 arc second, we said, was about 1/3600th of a degree. And so that distance from that star to the sun, if it produces an angle, a parallax angle of just 1 arc second, that's equal to 31 times 10 to the 12th kilometers, or about 19 trillion miles. So again, a light year was about 6 trillion miles. A parsec is about 19 trillion miles. In AUs, this is 206,265. And again, in light years, again, a lot more comparable. 1 parsec is about 3.26 light years. And again, the abbreviation, I didn't really put that over here, but you can see in this diagram or this table that parsecs are abbreviated PC. All right, so these are just some common objects, night sky objects, and it kind of shows you how far away they would be from each other. And so another thing, people sometimes wonder about the distance between the Earth and the Moon, because astronauts have made that trip before, and of course the Moon is the most prominent part of the sky that's not the sun. And that's about 1.3 light seconds. So if you could measure how quickly light travels, how far light travels in 1 second, light can go from the Earth to the Moon in 1.3 times that amount of time. And that also means that there's a bit of, again, radio waves would fall under this too. Radio waves can go the same speed as light. And so that means that any sort of radio communication between the Earth and the Moon, like with the Apollo missions, takes a little bit of a delay. It's a 1.3 second delay going to and from. Now, the sun and the Earth, this is a fairly common statistic. You may have heard this before, that the sun and the Earth are about 8 light minutes apart. So again, if you measured light going from the sun toward Earth, after 1 minute, it would have gone 1/8 of that distance. And then after 8 minutes, it'll have gone that entire distance. And that also means that 8 light minutes is equal to about 1 astronomical unit, 1 AU. Sun to the Neptune, that's funny. Anyway, the sun to Neptune, about 4 light hours. So Neptune is quite far. Like I said, I think it's about 30 AU away from the sun. The sun to Proxima Centauri. Now, Proxima Centauri is pretty significant because it's the nearest known star to the sun. And it says, like it says here, it's about 4.2 light years away. So the closest star, the light we receive from it moving at light speed takes about 4.2 years to arrive. The sun to Polaris, much farther, it's about 433 light years away. The sun to the center of the Milky Way, 100,000 light years away. And the sun to the nearest large galaxy, Andromeda, 2.537 million light years away. All right. This little diagram here just kind of shows you how parallax is defined and parallax angles, that kind of thing. We'll kind of revisit that idea a little bit more later on in the year. but I just wanted to include it in this lesson so you had one more reference to how, how a parsec is defined. And again, you can see it's defined in relation to the AU. Without the AU, you can't really define a parsec. All right, that's the end of today's lesson. Thank you for listening, and I will see you tomorrow.